precisely where needed. A dive into the exciting and emerging area of precision medicine. It's technologies that are going to revolutionize healthcare and tailor it to the individual. My name is Robert Spate. I direct the Engineering Biology Future Science Platform at the National Science Agency for Australia, the CSIRO. It's my great pleasure this morning to introduce our two speakers and my colleagues from the Global Future Council for Synthetic Biology. So first, Dr. Megan Frisk. She's the Director of International Affairs at the US Advanced Research Projects Agency for Health, or ARPA-H for short. Her role is to advance international strategy and collaborations for global benefit. Welcome, Megan.
Thank you.
Secondly, Dr. Faisal Khan. He's the Director and Principal Investigator at the Precision Medicine Laboratory in Pakistan's National Center for Big Data and Cloud Computing, spanning genomics, systems, and synthetic biology, and targeting oral cancer. He's got a strong history with the World Economic Forum, being a young global leader in 2019. It's my pleasure to hand over to our speakers to tell you about precision medicine.
Thanks, Rob, and thanks everyone for coming down. I think it would be nice to start off with what we actually mean by precision medicine. The NIH definition goes by using a person's information on their genes, environment, and lifestyle to be able to prevent, diagnose, and treat disease. So this clearly goes beyond just your routine clinical exams or labs and scans, and it delves deeper into what are those genes that underlie the disease that a person has, like, for example, cancer. In many cases, we also know the specific changes in each of those genes, mutations as we call them, that guides treatment, and it points at drugs that could be more effective in a particular disease in a specific patient. This offers a transformative new way of doing medicine in a very personalized manner. But cancer care is just one of those case studies that we can talk about. In many cases, for example, we're able to use information about your metabolic genes to optimize your drug dosage whenever you treat it. And one example from what we're doing in our lab with cardiothoracic surgeons, for example, is delving into mutations in some genes that influence the diameter of your blood vessels, something really important for heart disease treatment. But precision medicine is not just about improving treatment. It's also about avoiding ineffective treatment, which saves a lot of associated cost and pain, not just for the patients, but their households. And we all know a single incidence of such a disease in a family can push the entire household beneath the poverty line. So how has the field been faring over the years? We've seen a rapid and steep increase in the number of genomic data sets out there. This is just one large publicly available database. And we see an inflection point right after the Human Genome Project here. And it's a logarithmic scale, so it's exponential. And we see it getting steeper up here at the top. It's almost, the volume is almost doubling every 18 months, which is substantial. This is underlined by a more exponential drop in costs of DNA sequencing technologies. The same sequencing technology stack is being used to look into other molecules, like RNA, for example. A whole RNA-seq data set for a patient tells you about which genes are expressed, which are not, and if they are, how much are they being expressed in a particular situation. And in recent years, we've also seen the use of the same stack for single-cell sequencing. This is high-resolution sequencing, which looks at individual cells within an individual tumor and give us insights about a person's disease. And finally, with AI, I think it's getting even more exciting. We have data sets available in biology and medicine, and I'm really looking forward to how Gen AI is leveraged in the coming days. In Pakistan, we've launched our precision medicine pilot funded by the federal government through the Higher Education Commission. It's a modest start, but with a very strong conviction that we want to leverage these genomic data sets and tools, develop local data sets, and be able to preempt, hopefully avoid disparities that could happen in the future. Our focus for the pilot is on oral cancer. Pakistan is the 5th largest country in the world by population, and oral cancer stands right beneath breast cancer as one of the leading diseases in the country. We've also, instead of using a linear approach of looking at the genes first, we went on with a parallel approach by looking at layers of, by looking at a wide range of molecules, which gives us layers of complementary data sets that is richer to explore. Of course, we had machine learning experiments in mind, but again, with the advent of Gen AI, it's getting even more exciting. This entire multi-omic stack is backed by a biorepository, which banks all the samples, including patient-derived cell lines for each individual patient, offering a personalized preclinical model for follow-up studies. Over to Megan.
Thank you. So Faisal has talked about the why and the what, and I would like to talk a little bit about the how. Let's take a step forward. How do we make precision medicine a reality? How do we make it the norm? We need to make big bets on bold ideas if we're really going to transform this field and bring it into reality. We need to take that step forward and ask ourselves, what if? What if a single at-home test could save millions of lives by detecting cancer early? What if we could adapt cancer treatments even as the tumors mutate and change? What if we could 3D print a human heart in 1 hour, or a liver, or a kidney? And what if we could have our own bodies manufacture the cures for devastating diseases? How do we do this? How do we speed up this type of innovation? In the United States, we've launched the Advanced Research Projects Agency for Health, or ARPA-H, as this answer to speeding up innovation. We're using a business model that was pioneered by our sister agency, DARPA, the Defense Advanced Research Projects Agency. DARPA may be known to some of you as that agency that has given us things like the internet, or stealth and GPS technologies, or those early proof of concept studies on the mRNA vaccines that saved so many lives and livelihoods during COVID-19. So using this model, we're investing in what we call the high-risk, high-reward space, that in-between space. The space where the impossible ideas cannot be achieved by traditional biomedical research alone or by industry investment. Many of you may think of this in-between space as the valley of death. Probably heard that. We've taken to calling it the valley of opportunity. This is where we want to de-risk these wild ideas, these bold ideas. We want to be that investor in that middle space, take on that proof of concept or that minimum viable experiment that will really crack open a whole new field. But taking risk can make some parts of the health ecosystem feel unsteady or uncomfortable. And I'm not talking about casual or careless approach to risk. I'm talking about combining deep technical expertise with business rigor. And for that, we rely on special people we call program managers. Program managers come to us with their idea, their what-if question. They put resources behind it, and then they fund teams of performers, which are researchers in our lingo. We fund multiple shots on goal, diversifying our risk. Research metrics and milestones are tracked very rigorously over time, very short period of time. So we're a short-term investor, something close to 3, 4, 5 years. And we do not expect all solutions to succeed. Some may be ahead of their time. We may need to reallocate funds along the way. Program managers may halt work that is failing, but what they will do is adjust course as necessary. At only 2 years old, we've already started making some very pivotal investments across the entire spectrum of human health. But what I want to share with you is just a couple of the ideas, those what-if statements that I'm talking about, a couple of those specific to the precision medicine field. One program is called ADAPT, Advanced Analysis for Precision Cancer Therapy. ADAPT is really looking at the current cancer treatment landscape for metastatic cancers. Right now, a very limited number of measurements are taken on a tumor and used to inform treatment decisions, and often not updated to reflect the tumor as it mutates and changes. What ADAPT will do is fund those teams of researchers to take many different types of measurements of the tumor, including omics, be able to combine those with advanced computational tools, artificial intelligence, machine learning, mathematical modeling, and what we hope comes out the other end is a set of biomarkers that will better inform treatment decisions and improve survival and outcomes in patients with metastatic cancers. Another program is called Embody, Engineering the Immune Cells Inside the Body. This is really taking a look at cell therapies today and how much potential they have, but how inaccessible and costly they are for us. Right now, traditional cell therapy approach is very technically complex. It requires substantial patient involvement. It's very costly. It's around $100,000 per dose per patient just to produce. It's time consuming. Many patients die while waiting for these cell therapies. And fourth, it's not very accessible. In the United States, these cell therapies are available in fewer than 2% of clinics and hospitals. So what Embody seeks to do is develop platform technologies that will engineer or edit the cells inside your body and be able to respond to disease cues and produce the therapies or the treatments that are needed. If we're able to do this, well, we can remove most of those barriers to cost, time, access, manufacturing, and so forth. As I mentioned, we're funding a gamut of work across the health research, or across the health and healthcare spectrum. These were just 2 examples, but what we do expect is that when we succeed, everyone stands to benefit.
To be fair, precision medicine's idea has been out there for a while now, which begs the question, why haven't we seen wider adoption? But we saw it's not technological barriers that are limiting us. It's perhaps broader systems level challenges that lie outside the laboratory. From our work in precision medicine in a rather nascent ecosystem, I'd love to share some early lessons that we have. In many cases, the government might not be the main driver in such large projects. It might take groups of progressive science leaders on the ground that could do their job. We need to be open to new ways, new non-traditional ways of rallying coalitions and consortia to execute such projects. No single entity is able to pull something like this off. We need multiple teams across multiple sites that are interdisciplinary in nature and have a wide range of skill sets. This means we require team science, and we need to build critical masses around projects like precision medicine. There's often a temptation amongst policymakers to take such work everywhere, but we see value in building densities and creating synergies in a more concentrated manner. Sometimes things go much faster if they're housed outside the usual structures, like we saw with ARPA-H. This could be another innovation in terms of execution. Consumables and perishables are one of the biggest challenges in doing biomedical research in a developing country context. I'm fully aware that something like this is totally taken for granted in established labs across the world. But this means governments need to innovate their public procurement processes, and perhaps vendors have a bigger role to learn from local nuances and help enable more and more research on the ground. Many of these large, fast-growing cities across the developing world have pockets of densities or economic clusters that could be leveraged. In healthcare, for example, these are amazing grounds for rigorous, large clinical studies and trials, including projects like precision medicine. This is not just in terms of size and volume, but also diversity. The diversity of people who show up at these clusters in terms of genetic background. Many of these clusters are brimming with sharp and smart young talent, which needs to be leveraged. Countries like Pakistan, for example, my province, 70% of the population is below the age of 30. These include some really smart doctors, data scientists, and biologists, which is exactly what you want for interdisciplinary projects like precision medicine. Over to Megan.
Okay. Faisal's absolutely right. It makes no difference if everything that we invest in ultimately just sits on a shelf. We need to have the right structure around the research to enable that transition potential, be able to translate these types of inventions in precision medicine into the real world. So at ARPA-H, we have taken this into account and really built some key features into the function or the operations of our agency. One is to ensure that the programs are designed with that translation potential in mind, thinking about the market, thinking about the patients, understanding the potential trajectory, not just in the United States, but also around the world. Two, making sure that we're sourcing ideas from everywhere. We need to bring fresh ideas, novel ideas, into the pipeline as well, so that we can have innovation that reflects everybody. So how do we do this structurally? For programs that I mentioned, like ADAPT or Embody, to survive in the wild, is what we say, or go on to live in the real world, they really need other stakeholders to meet them where they are. We're funding the researchers to go after these risky ideas, these big problems, but we need others to come to the table and meet them where they are. So we see ourselves at ARPA-H as a catalyst, not the only solution, the catalyst within this wider ecosystem. So we very intentionally work across our own government, other funders within the government. We need to work with industry. We need to work with investors. We need to work with the international community. So we're here to collaborate and make sure that the solutions that we are investing in actually come out and impact patients' lives. But we're a small agency. We're really only, I think, around 200 federal employees. So how do we do this at scale? How do we know what patients want or need everywhere, what doctors will use everywhere, what investors will invest in anywhere? We have created and launched a hub and spoke network to do exactly this, to reach out into the communities. We have a hub in Dallas that's meant to engage customers, doctors, patients, providers, community health workers, and a hub in Boston that's meant to engage the investor community, to help us understand that commercialization potential. With these 2 hubs, we have, I think at this point, over 900 spokes, not just in the United States, but around the world. And these are public and private and non-government entities that are willing to work with us on these game-changing solutions. The second point I made about fresh vision and voices, solutions can come from anywhere, and we want to bring them to us. So lots of entities that are smaller, small companies, labs, nonprofits, they may not know how to do business with the US government. So we need to lower that barrier to interact with us. So we're not only innovating in the research, we're also innovating in the way we do business. So take, for example, our Sprint for Women's Health, which we launched earlier this year. I know it's not a precision medicine example, but our Sprint for Women's Health that we launched earlier this year. We asked for only a 3-page abstract from proposers, not a 150-page one, not one that's going to take months to write, hundreds of thousands of dollars or resources to put behind it, a 3-page abstract. And from there, we could select which abstracts or which solutions that we wanted to pitch us. From there, we can select the winners. They'll be announced very soon. So we're making decisions quickly, nimbly, flexibly, working with the community. And we think we've achieved what we set out to do, which is lowering that barrier. We received solutions from 34 countries, in addition to the United States, within the United States from 45 states, plus the District of Columbia. And of those submissions, over 40% of them were from entities with fewer than 10 people. That's lowering the barrier, and that's bringing those innovative voices to the table. So we started this meeting yesterday talking about hopefulness. So what I wanted to leave you with was a hope for the future of precision medicine. What does it look like 10 years from now? 10 years from now, maybe we're all back here at the World Economic Forum talking about precision medicine as a reality, not a question mark, whether we will be able to do precision medicine, but that we actually are doing it. And we're sitting around talking about the precision therapies that we've each received and how it has impacted the lives of ourselves and of our loved ones. The next step in getting to that reality is to take a leap of imagination and embrace risk. Because remember, the patients are waiting. Thank you.
Thank you very much, Megan and Faisal, for a fantastic overview of both the technology, but also the deployment and social aspects that are inherently important if these technologies are going to see the light of day. We have about 10 minutes for questions. I've got several. If anybody's got a burning question in the audience, put your hand up. But I'd just like to start. I think it's very inspiring, Megan, where you talk about the networks and the global engagement and the potential of this technology to be deployed globally. But what does that global landscape look like? Who's engaged around the world? Who's doing what? What does it look like?
Yeah, it's a great question. I think owing to a lot of the things that Faisal mentioned at the beginning in terms of the lowered cost of sequencing, the accessibility of the technology, and I think so many governments around the world and private sector recognizing the vast potential of precision medicine, I think we're seeing an uptick in investments and interest in these national level genome initiatives, sequencing human genomes across the world. Of course, we have this in the United States. There's a program, of course, in the UAE. We also see this in Singapore and in Japan and in Denmark, the UK. So these countries, Pakistan, these countries are really all over the world investing in genomic medicine.
And are these connected? as well, or is that something for the future?
Yeah, I think it's something we do more and more here in the future. There's quite a bit of collaboration and connectivity, and I think Faisal could absolutely speak to that. But if we want to make sure precision medicine is representative of patients all over the world, we need to bring this data to bear on these solutions, and that looks different everywhere. And so how do we collaborate to make that a reality?
Yeah, Faisal, do you want to add anything to that?
Yeah, so I mean, the earlier bit is about data generation, right? When you do undertaking the genomic part of it is basically creating the data set. I think the actual excitement then begins after that when you begin to analyze the data. I think that's where collaboration will be even more critical and exciting from a scientific perspective as well. So I think all eyes on the downstream analysis and how countries begin to talk to each other and share these resources.
So this is kind of, it's a big data play, isn't
Absolutely.
it? You talked about the stack and all the different types of data. We're talking about people's genomes as well. On one hand, we need collaboration, I guess, to aggregate data sets so we can learn, we can train AI, things like that are going to help. But what are considerations on the flip side of that around security and equity around the data? How do we ensure that this is equitably deployed and managed going forward?
There is broader consensus on the patient privacy part of it. I think across the world we see the consensus that has to be taken care of. And there are standards in place on how to do that. Some hospitals are very open about it. Others sign up patients at every footfall. So there are varying models people can adopt. But I think the biggest challenge will be how do we get access to a worldwide genomic data set which is representative of different ethnic backgrounds. I think that's the key challenge. How do we enable countries which are not yet investing in these technologies to be able to come up and share their genomes in the broader pool? Because for me, that's the source of all the inequities. If these populations are left out, that's, I think, not a great trajectory to be on.
Yeah, so there's deliberate steps that are required to do that. I was wondering as well, Megan, from ARPA-H's perspective, is that equity piece something that you build in to the programs?
Oh yes, and I didn't talk about it, but equity is really at the core of everything that we do. And to exactly what Faisal is saying about making sure that the data are representative and coming in, one feature that we can use with ARPA-H is getting out into those patient communities, being able to bring more patients from more geographies across the United States into clinical trials and into these investigative studies. And so that's one of the ways that we can leverage that type of network. But we also build in considerations around equity and access and cost and risk and time. We build these into the program design. So program managers actually have to pass a series of questions that are called a Heilmeyer catechism. And these questions ask them all these things that they build into their program and make sure they're funding it with that equity piece in mind. And that's equity on the way in. We also need to think about equity on the way out and making sure that patients all over are able to have access.
Because we're talking about different business models for healthcare, really, going forward, building on traditional healthcare and pharmaceuticals, and making sure that this is very exciting technology. It's going to mean that patients aren't getting drugs that don't work. It's potentially cost savings as well, but at the same time, there's technology complexity, there's more testing, there's tailoring of drugs, and so on.
That's right.
So what do the business models look like? Maybe Faisal, going forward, how does healthcare look different going forward?
So I'm very keen to see how these data sets will be leveraged by the broader drug development community. I think that remains to be seen. For me, I think the first piece is, obviously, when you have the data set, there's no point sitting on it. I mean, agility comes in as well. I mean, you need to plug that into the drug discovery research worldwide to be able to see some representation of your population in the upcoming drugs in the market. So for me, that's one bottleneck to crack at and to think about for us globally on how can we leverage these new data sets that are coming up.
Yeah, no, great. So as I said in the introduction, we're from the Global Future Council for Synthetic Biology, and we define synthetic biology as the tools and knowledge that allow us to engineer biology for a variety of applications. Megan, you mentioned around cells being reprogrammed and put back into biology. That's the synthetic biology technology. But really, what is the role of the engineering of biology or synthetic biology in these new therapies going forward? There's a few more examples that you can pull out.
Certainly. So the one you're referencing is Embody, the program that's trying to reprogram immune cells within your body. And of course, that's going to need new tools. First, you have to get into the cells very specifically, then you have to be able to reprogram them in vivo, meaning inside the body, and then have them react to certain cues and deliver therapeutics. That's no small feat, and something that we still need to perfect that technology. So that program will take that on as part of a bigger endeavor. And that's the therapeutic side. You can also envision synthetic biology, and we actually have a program in this space too, called Poseidon. It's relatively new, using synthetic biology as the basis for sensing, as the basis for being able to detect disease. So there's the detection piece and the treatment piece.
So that drives down the cost of the detection aspect for precision medicine as well.
I think we would hope that it gets to that point, yeah, but Faisal?
Yeah, so for me, microbiomes are super exciting. I mean, when you think of the ability to be able to reprogram those bacteria, and
what do you mean by microbiomes? You mean in the gut? Or?
We all know more bacterial cells are present in and on our body compared to our own cells. That's the whole sort of domain there. And if you're able to engineer different pockets of that in the gut, or in our case, in the oral cavity, for example, you're able to develop drugs that are responsive when a disease is there and passive when it's not. So it becomes a very exciting avenue for treating disease in a more precise manner. Another one's biosensing, for example. If you know the exact variants in a gene, you're able to pick them on using lower cost, perhaps cell-free diagnostics. That's another exciting area that we're also interested in terms of diagnostics.
Yeah, they're both great examples that really speak to working with the human biology as opposed to interacting with it, with a drug. It's actually using the biology, working with the microbiomes, for example. It's a different way of considering how drugs are delivered or even therapies work.
Yep.
So I think it's an exciting future going forward. We are out of time, so I'd just like to thank Faisal and Megan for a fantastic overview of precision medicine. Feel free to try and catch them after this if you want to talk and meet with them. And thank you for coming to this Betazone.
Thank you.
Thank you. This is nice.